So good afternoon. My name is Dr. Richardson. This is lecture 13 of the course entitled An Introduction to Linear Algebra Using Python. This is the final lecture for the course. My email address is listed below, srichards22@comcast.net. So you're invited to send me questions either on the lectures, problem set solutions by email. You can do this anytime, even past the summer. Excuse me. And it's the plan to get the entire course updated and establish a link where all this course material will be available on YouTube. So again, a reminder that learning is not a passive activity. It's important not just to sit back and hope that by osmosis, you'll be able to grasp all the concepts of this course by just looking at the video lectures. You need to take notes in real time, either by looking at the video clips or the lectures in real time. It's important to write down the steps, go through the logic of what we're talking about. Problem sets are critical. You won't get anything out of this course without doing the problem sets. And again, there are 13 of them. I would not advise you to simply work backwards and look at the solutions and try to re-engineer to the original question. It's fair game to look at part of the solution if you get stuck, but just do that by taking a piece of paper and going through the solution to get some hints. Again, my email address is listed, so you can use that if you have questions. And you're invited to use a ruler for today's lecture as well as other lectures, assignments, things like that. Okay, so last time we were looking at the problem of the projection of a point which we'll call B. This point is also a vector. Vectors are points on a plane. And back in lecture 12, we actually took the time to, I misspoke, jumped ahead of myself. Let me look at first a review of the question of projecting a point on a line. And I'll get to the plane in a minute. Okay, so remember what this problem entailed. Here's a vector. Another vector. So this vector is A, this vector is B. And the question is, if you drop a perpendicular line down to the vector A, you can create this vector, which we call the projection of B onto A. Now you can certainly take a ruler and measure this, but we want to do this analytically. And so we showed at least two different ways that the projection of the vector B onto the line A is given by this interesting expression. So all you need to know are vectors A and B. This creature in a dotted line, inside the dotted line, a loop, is really a matrix divided by a scalar. So it is a matrix. We defined it to be the projection matrix. And it is simply A times A transpose divided by A transpose A. The numerator here is a matrix. A times the transpose of A is a matrix, whereas A transpose times A, that's a scalar. So in fact, we discovered last time that the projection of a vector B onto a vector A is just the projection matrix times the vector. This thing on the right-hand side is an example of matrix vector multiplication. So it gives you a vector, which is what you see on the left-hand side. Okay, it's one thing to write down these expressions. It's another thing to figure out what they mean and get comfortable with them. And that's the purpose of the problem sets. So there are lots of examples in problem set 12 and problem set 13, where you're asked to look at the projection of a point or vector B onto a line, A in this case. And I invite you to look at those exercises. So the last thing, or last time, we also looked at a different question, named the problem of projection of a point or vector. Vectors are points, points are vectors. Again, we'll use the symbol B. And in this case, we're going to project this point or vector onto a plane. A completely different problem that we looked at last time. So let me remind you geometrically what's going on here. Here's a vector B, and it has not one, but an infinite number of projections. So there are infinite number of projections of B onto this plane. Sorry. So in fact, we want to find the projection, this thing in question mark. We want to find this vector in our plane. That is in fact closest to B. So remember, our plane has in it a set of linearly independent vectors. So the plane is spanned by linearly independent vectors, A and A1, A sub 1 and A sub 2. The coefficients that we'll use to generate points in the plane will be A sub 1 and A sub 2. And we showed last time that in general, all points or all vectors in the plane are generated by this linear combination, where A is simply a matrix whose columns are the linearly independent vectors A sub 1 and A sub 2. So we could say that any point in this plane is defined by A, the matrix A acting on the vector X. What we want is the vector, the projection on the plane that is closest to B. And let's draw the figure again. So here's our vector B. Our plane is just determined by this matrix vector multiplication. And we're going to call the projection of B onto the plane the vector that satisfies this condition. Where X asterisk is a very special vector in the plane. So this is closest to B. So in fact, we showed last time that A times X asterisk has to satisfy the following equation. Namely, the transpose of A times B minus A times X asterisk has to equal, in this case, the zero vector. Or you could rewrite this as A transpose A X asterisk equaling A transpose of B. We're here. So we showed that this was true back in lecture 12. You can clearly rewrite this. And this particular equation has a name. It's referred to as the normal equation. So again, the goal here is to find X asterisk. So that's relatively easy, right? We take this creature here, take its inverse, and then left multiply both sides of the equation by that inverse. And we get X asterisk equals the inverse of this product, of this matrix product, times A transpose B. And now our projection of B on the plane is simply given by A times X asterisk, which is going to be A times the inverse of this matrix product times A transpose B. So you can see here that it's convenient. We're doing this in analogy with what we did before with the case of projecting a point on a line. We will define P as our projection matrix. And in this case, it's A times the inverse of this matrix product times A transpose. And we have our final result. Namely, the projection. So let's put this in a square. These are all fundamental equations we're deriving, or we would derive last time. I'm just reviewing. So the projection of B on the plane that is closest to the point B is simply A acting on X asterisk, and that equals the projection matrix times B. Okay, take a deep breath. This looks involved, and it looks like we have a lot of matrix algebra to do, but trust me, this is much easier to do than to try to use geometry to draw pictures of this system, the plane and B, and then figure out what that projection of B on the plane is. So at this point, let's tie all these ideas together and let's go through an example. Okay, so the example I want to use starts with two vectors. We'll call them V sub 1 and V sub 2. Here they are. These are vectors in 3 dimensions. They are vectors in R3. I want to check some things about these vectors. So, or one thing at least about these vectors. It should be obvious that these vectors are linearly independent. That is to say, C sub 1 times the vector V sub 1 plus C sub 2 times the vector V sub 2 can equal the 0 vector. And the question is, under what circumstances is this true? We've seen this drill before. Essentially, C sub 1 equals 0. You get from solving this matrix equation, C sub 1 plus C sub 2 is 0, and C sub 1 plus 2 times C sub 2 is 0. So all of these tell you that C sub 1 and C sub 2 all vanish. So these vectors are linearly independent. So the next thing we want to check or say about these vectors is the following, that since they are linearly independent, they span a plane. They span a plane in R3. So if I draw a nice little picture, here's the plane. A sub 1 and A sub 2 are somewhere in this plane. Here's an origin, and here's B. So it's useful to remind ourselves of some things we talked about last time. And again, if you're rusty on this, you have lots of practice exercises in the problem sets. Let me remind you about the equation of a plane. Excuse me. It satisfies the following equation, where A, B, C, and D are constants, X, Y, Z, and X, Y, and Z are variables. And if the plane, in fact, passes through the origin, which we have said it, we've defined it to be in our example, then in fact the equation of the plane is just AX plus BY plus CZ times Z equals 0. And I won't do this, but I'll let you prove this, that in fact, for this example, namely for the case of A sub 1 equaling this vector and A sub 2 equaling that vector, then in fact, the equation of the plane that we're looking at in this problem satisfies that equation. Okay. So let us find the projection of B onto this plane, which satisfies this equation. So, how do we tackle this problem? Well, we showed, as a review today, and we showed last week, that the equation that you're going to need is the normal equation. And let's call that equation star. And we have shown that you could also write the normal equation in this form. And let's call that a double star. So this is where we're going to start our solution at. But equation star is easier to work with than equation double star, since the former, equation star, does not involve calculating the inverse of a matrix. So this is a very important point that we've seen many, many times throughout the course. If you have a choice between taking the transpose of a matrix, as you do in equation star, or the inverse of a matrix, as you do in equation double star, you always pick the former. It's much easier to just deal with transposes of matrices as opposed to an inverse of a matrix. Okay, so having said that, let's write again the normal equation. Transpose of A times X asterisk equals the transpose of A times B. What do we know? So we're given A, which again is just a matrix whose columns are A sub 1 and A sub 2. We're also given B, and so we need to find, this is a transpose. Again, I never want to make the fusion between the transpose of a matrix and its Hermitian conjugate, or that's a dagger. So we're going to need to find two things. We're going to need to find the matrix product of the transpose of A times A. We're going to need to find the transpose of A times B. And then finally, we're going to need our answer. That is, what is A asterisk? So let's go through this one step at a time. So in our menu of things to do, the first thing we need to do is figure out, that's terrible notation. We need to figure out what A is. And that's pretty easy, right? We were told A sub 1 and A sub 2. And so here they are. So this is a 3 by 2 matrix. It's a tall matrix, has more rows than it has columns. The next thing we're going to do is find the transpose of that matrix. And so that is simply this, which is a wide matrix, it has more columns than it has rows, and has 2 rows and 3 columns. So it's a 2 by 3 matrix. You know, I think it's always helpful when you tackle problems, just break them up step by step. And, you know, the more problems you do, then these steps become secondhand, but set this thing up. Next thing we're going to do is we realize we're going to have to know what this creature is in the dotted circle. So we need to figure out the transpose of A times A. And again, that's just an exercise in matrix multiplication. Again, the nice thing about this final lecture and the discussion of the least squares approximation is we're going to use all the tools, a great deal of the tools that we've discussed in the course heretofore. So transpose of A is a 3 by 3 matrix, 2 by 3 matrix, sorry. And A is a 3 by 2 matrix, so these two guys are compatible for matrix multiplication. So the result should be a square matrix of order 2. And you can verify that's what it is. Excuse me. Okay. Next, we go down our laundry list. We need to calculate the transpose of A times B. And that's pretty straightforward. Again, I misspoke earlier. The transpose of A is a 2 by 3 matrix, not a 3 by 3 matrix. So I'll just rewrite that. That's 2 rows and 3 columns. B, she is a 3 by 1 matrix. So these guys are compatible for matrix multiplication. And the result is a 2 by 1 matrix. Okay. So again, what is the normal equation? And let me give you a way of remembering what the normal equation is. You start out with A times X asterisk equals B. That should look familiar to you. But X asterisk is a very special vector. It's the vector that is closest to B. So to get the normal equation, all you do is left multiply both sides of this equation by the transpose of A. That's the normal equation. Now, evaluate this guy. What is it? Well, I know what A transpose A is, and I know what the right-hand side of this is. So I have a square matrix of order 2. A asterisk has 2 components. We'll call them A asterisk 1 and A asterisk 2. And the right-hand side is a 2 by 1 matrix we've already calculated. So we've seen this type of problem before. We want to find these unknowns, X sub 1 asterisk and X sub 2 asterisk. So solve for X sub 1 asterisk and X sub 2 asterisk using Gauss-Jordan elimination. Okay, so we can almost do this in our sleep, but we got to be careful. So here's the augmented matrix, and I want to find the appropriate elementary row operations to put it in a reduced row echelon form. Okay, first thing I'm going to do is take row 1 and divide it by 3. I'll get the following 2 by 3 matrix, and I get a leading 1 in the first row. The next thing I want to do is take row 2 and divide it by 3. And row 1 is not changed, but row 2 is changed. Let me take a Xerox copy of row 1, multiply it by -1, and add that result to row 2. So row 1 is not changed, but row 2 is definitely changed. And I've placed a 0 underneath the leading 1 in the first column, which is a good thing. Let's take row 2, multiply her by the factor 3/2. That's going to give me an unaltered row 1, but row 2 is going to look like this. So we're almost at the stage of reduced row echelon form. So finally, let's take a Xerox copy of row 2, multiply it by -1, and add that to row 1. And what I have is the result of Gauss-Jordan elimination. I have my augmented matrix in reduced row echelon form. So the corresponding set of algebraic equations can be written down starting from the bottom, working our way up. A asterisk sub 2 will be -3. And A asterisk sub 1 is going to be 5. So X asterisk is just this vector. Okay, so I am now in a position to answer the question. What is the projection of B on the plane? Well, the projection of B on the plane is given by this expression, where A asterisk is in fact A times X asterisk is a linear combination of the linearly independent vectors A sub 1 and A sub 2, and the coefficients are A sub 1 asterisk and A sub 2 asterisk. So this projection is just 5 times A sub 1 plus a -3 times A sub 2, and that's 5 times 1, 1, 1, -3 times 0, 1, 2. So the projection of B onto the plane is this vector, this 3×1 matrix, written as follows. And that is your answer. So it's useful to go through many examples, and I've given you an ample supply, both in problem set 12 and 13, of practicing this exercise. And the more you practice it by going through examples, the more comfortable you will be in dealing with the normal equation in terms of what it means and how it's useful. So there's a final point I want to make. I'll call this 8. There's a new concept I want to introduce. My apologies. And this new concept can be illustrated by looking at my plane. Here's my vector B. Here's some origin. Here's my vector B. As we discussed, the projection of B onto the plane is this guy, which we'll call P. There are an infinite number of projections, but this is the one that's closest to B. So trigonometry will tell you that in fact, this vector is B minus P. So let's just pull that out of the picture so it's clear what's happening here. And we just use the laws of vector addition. You can prove to yourself that that's right. So this guy, B minus P, I'm going to give it a special name for reasons that will be clear before the end of today's lecture. I'm going to call this the error. So in fact, in this problem here, you can calculate what this error is. I'll put it in quotes. That's just a word, 5 letters. It has to do mentally with the concept of error we'll worry about later. So this is B minus P. And I know B and I know P. So it's simply a vector in R3 as a matrix that has 3 rows and 1 column. So I'll give you 2 assignments to check. It's clear from trigonometry that the error B minus P should be perpendicular to either one of the initial vectors, these 2 linearly independent vectors, a sub 1 and a sub 2. And that's easy to check. So I'll leave that to you to check. What may take a little bit more skill is to prove that the projection of B onto this plane is in fact given by calculating the projection matrix first, and then multiplying it by B. And remember, the projection matrix is just a function of, if I can use that word, or it depends upon the vector A and the transpose of A. And so this is a little bit more work, but you should, in fact, check that. So at the end of the day, calculate the projection matrix, act on it with a B, and show that you should get 5, 2, minus 1. Okay, again, I've said this before, there's no problem with reiterating. You need to go through examples, you need to go through exercises to see how all this works. Okay, so all of this is nice, but how is it useful in practical applications? And that's a fair question. And like most fair questions, it deserves a fair answer. This is applications, right? Okay, So let's go back to a problem that we looked at, back in lectures 4 and 5. So we want to solve a system of linear equations simultaneously, and that reduces just to solving this matrix equation, where you have a matrix A that is known. You have a constant matrix on the right-hand side, and that's known. And then you have a vector of unknowns. And the task is to solve this problem, to find X. And we've gone through many examples of this. So I'm going to pick a particular problem. I'm going to pull out of the air the vector A. In this case, this vector is matrix. I'm going to pull out of the air a matrix A. This matrix is a tall matrix. He has 3 rows and 2 columns. And I'm going to pull out of the air a vector B. It has 3 rows and 1 column. And you can see that A times X equals B. Excuse me, you're going to have compatibility when you do the matrix multiplication. So X has to be a 2-by-1 matrix. Excuse me. So this is a problem that we've been looking at throughout the whole course. We've been doing this many, many times. Let's find X. And the way we'll do it is through Gauss-Jordan elimination. And by now we're experts in this, at least for simple problems. For more complicated problems, then you have to do this using Python or Mathematica or MATLAB, or if these matrices are huge, large, then on some type of supercomputer. Okay, so the augmented matrix looks like this. It's a 3-by-2 matrix, sorry, misspoke. So I would start out by taking a 0x copy of row 1, multiplying it by -1, and adding that to row 2. And I would get the following result. And the goal in Gauss-Jordan elimination is to get your augmented matrix in reduced row echelon form. So the next thing I would do is take a 0x copy of row 1, multiply her by -1, and add that result to row 3. And row 3 becomes changed. Row 1 and row 2 are not altered at all. Let me divide row 3 by 2. Let me take a 0x copy of row 2, multiply him by -1, and add the result to row 3. And lo and behold, well, I'm almost there, right? Let me divide row 3 by 3. Let me take a 0x copy of row 3, multiply her by 6, and add that result to row 2. Row 1 is not changed. Row 3 is not changed, but clearly row 2 gets changed. And then the last thing I want to do is take a 0x copy of row 3, multiply it by -6, and add that result to row 1. And this is, I've written the augmented matrix in reduced row echelon form. So the corresponding, let's see, oh, that looks fine. So the corresponding set of algebraic equations what is this? Starting from the bottom and working my way up. 0 times x sub 2 has to equal 1. X sub 2 times 1 is 0. And x sub 1 is 0. And you see that the first of these guys is a problem. There is no value of x sub 2 that satisfies the first equation. So there's no value of x sub 2 that satisfies this equation. So we would simply say, oh, okay, this is not unlike any problem that we've seen before. Here's a case where there's no solution to this particular example, where matrix A is this, and the constant matrix B is that. And, you know, up to now, we would just stop and say, okay, we take our marbles and go home. But now we're going to go back and look at this problem in a new light. So there's no exact solution to this problem, but maybe there's an approximate solution. So let me step back and see if I can wrap my head around this. If there is an exact solution, so if there is a, or if there is a unique solution, then you should be able to write down this equation that A times X will equal B. If there is no solution, or let's spell this out a little bit more carefully. If there is a unique solution, and A acting on X minus B should give me the 0 vector. So if A times X equals B has no solution, then in fact, A times X minus B is going to be equal to some finite number, not going to be 0. So let's look at this problem geometrically. Here's my origin. Here is one of the linearly independent vectors, A sub 1, that spans the plane. And here's another linearly independent vector, A sub 2, that spans the plane. If B is not a vector that satisfies this equation, then all we're saying is that you cannot take B and write it as a linear combination of X sub 1 and X sub 2. Now go back and look at this diagram. What that also tells you is that B is a vector that's not in the plane. So perhaps some lights should go off in the back of our head. We cannot solve, in this problem, this matrix equation. But we can find a value for x, which we'll call x asterisk, that gives us the closest solution to the problem. Another way of saying closest, it's the best solution that we can get as an approximation. So go back and look at this plane. Here is B. We can't find A times X, but we could find A times X asterisk. Such that A times X asterisk minus B is going to be the error in this problem. And it's going to be as small as possible. So there are lots of times in applied math and science and engineering that you can't solve problems exactly, but you can solve them approximately, and you can run with that. Just because, you know, Gauss-Jordan says no solution doesn't mean we need to go run home and hide. We can do better, and we will do better. And our exact solution is something we'll call the least squares solution, or the least squares approximation. So let's underscore that. So in fact, the least squared solution, so let me restate this differently. We cannot, in this problem, solve this matrix vector equation. There's no solution to that. But we can solve this equation, and we can find the least squares solution. Why we call it least squares, we'll talk about that momentarily. So, how do we find X asterisk? I may refer to this as a star as an asterisk. Well, let's go back and look at some of the machinery we already talked about in this lecture. Our normal equation says that the least squares solution has to obey that equation or this. This is our normal equation. So if we can solve this for X asterisk, we can obtain the least squares solution to the problem. Okay, so clearly, to see how all this is hanging together, we're going to have to go through some examples, and we'll pick two examples. But before our break, I want to go back to a problem that I've been hiding. Why is this called the least squares? Solution or approximation? So that's the question. Here's the answer. In this problem, we want to make the error, in order for this projection of B onto the plane to be as close as possible to B, the error must be, the norm of that vector must be as small as possible. Well, how do you calculate the norm of a vector? You take its dot product with itself, and you take the square root. So the square of the norm of a vector is just the vector dotted into itself. So to make our notation a lot simpler to follow, let us define the vector C as A times A asterisk. So this error is just C minus B. And actually, we'll look at the error squared. This is the dot product of the vector C minus B with itself. And that is simply C sub 1 squared minus B sub 1 squared plus C sub 2 squared minus B sub 2 squared. And that goes all the way up to the number of components that you have in your vector. And you can see that if you want this error to be as small as possible, which it is, then the sum of the difference of these squares C sub I and B sub I must be as small as possible. Hence the term least squares. Solution or least squares approximation. Okay, so we'll take a break now. Let's take a break for about 10 minutes, and then we'll come back and we'll look at two examples of the least squares solution scheme, or the least squares approximation. And again, as advertised before, this is a nice problem to look at from a practical point approximation, from a practical point of view, but also at least as far as this summer course is concerned, these 13 lectures, it's going to allow us to pull together everything we already know about linear algebra. Okay, so let's take a break and see you in about 10 minutes. Okay, so let's start. So as advertised, I said we would go through some examples. And let me make the following point. Spent a considerable amount of time going over the formalism for the least squares approximation. Or to find a least square solution. And we're going to go through two examples, at least two. And you may ask the question, well, why shouldn't I just take the formalism, the final equation, memorize it, and just use it for the examples? And the answer is no. You got to do both. You really need to go through the steps in the formalism and make sure you understand it. And then go through the examples. It doesn't suffice just to take a final equation and just plug in numbers and say, okay, I understand the concept. And most importantly, the formalism is extremely useful because it essentially goes through many of the key ideas we've talked about in this course so far. All right, so let's go through our first example. So I'm going to give you 3 lines. And in order to tell you what those lines do, I need to give you their equations. So here's an equation for line 1. Here's an equation for line 2. And here's an equation for line 3. And I've written them in the form of the general equation of a line, y equals mx plus b, where m is the slope of the line and b is the y-intercept. So I can actually plot these lines. Here's again where my ruler is useful. So here's the x-axis, here's the y-axis. Two of these lines clearly have a negative slope and one has a positive slope. So line number 1 is going to intersect the y-axis there. And here is a point where x equals 1. And I point that out, no pun intended, because that will describe line 3. And then there is another line, just sketching these guys out roughly. You can do this more precisely. Where this is line 2. And clearly the lines 1 and 3 intersect. Clearly lines 2 and 3 intersect. And you can find out what these intersection points are. You can solve that yourself. So here's the question. What is the point where all 3 lines intersect? Okay, so it's pretty straightforward to look at this plot and get that answer. But let's not tackle the problem that way. Let's just look at these 3 equations, which define these 3 lines. This gives us data, some information, and let's recast that data as a matrix equation in terms of unknowns and knowns. So here is a matrix which we'll call A. She has 3 rows and 2 columns. Here's our unknown matrix A, X. It's 2 rows and 1 column. And my constant matrix B, again, by the classical rules of matrix multiplication, this has to have 3 rows and 1 column. Okay, so you could solve this problem by using Gauss-Jordan elimination, as we've done previously in this lecture. So you could solve for the unknowns using Gauss-Jordan elimination. Okay, just hold on 1 second, please. Okay, some minor technical problems, but we're okay. And what you'll find is what you expect, that no solution will exist. So no solution will exist for this problem. And I'll leave it up to you to, in fact, verify this. But I didn't have to go through all that work. If I just look at this plot, I can see that these 2 equations will not have a common intersection point. So this system of equations has no solution. But I don't give up and go home. I ask myself, is there a least squares solution? That is to say, well, the answer is yes. And that is, can I solve this equation and not find x, but x asterisk, where x asterisk is the least squares solution to my problem. So how do I go about doing that? Well, it's pretty straightforward. We've gone through the great discussion of projections of points on lines and points on planes so that we can understand where this normal equation comes from. And we can solve this normal equation and always find a least squares solution, provided we know what A is and B. And so we want to find the least squares solution to the problem. And that's just figuring out what the components of this 2x1 matrix are. x sub 1. I don't need the subscripts. This x and y will suffice. Okay, so we know how to do this, right? A is just the following 3 by 2 matrix. I'll need its transpose. I will need to calculate the transpose of A times A. So that's just this matrix, which is 2 by 3. And I need to multiply that by a 3 by 2 matrix. These matrices are compatible. So they're going to give me a 2 by 2 matrix, which is this. It should not surprise you that this result is that of a symmetric matrix. And you should think about that for a moment as an aside. Go back to some of our earlier lectures and problem sets and see why that's not unexpected. Okay, the other missing part of the puzzle is B. Excuse me. So we now have our normal equation. Which is A transpose times A times the least squared solution equals A transpose times B. And I've got everything on the left-hand side. I have everything on the right-hand side. So let me just simplify the right-hand side. And here's the matrix equation that I want to solve. I said this before, let me say it again. I always want to differentiate my notation between the difference of the transpose of a matrix and the Hermitian conjugate of a matrix. They're not the same. So the former is capital DT, the latter is a dagger, and my notation should reflect that. Okay. Now this problem here we can solve by just using our time-honored trick of Gauss-Jordan elimination. So let's do it. The augmented matrix is as follows. So let's write this in reduced row echelon form. So let's interchange row 1 and row 2. Again, these are all skills that we've worked on developing in various stages of the course. So it's wonderful. Come back and use them again. Next thing I'll do is take a 0x copy of row 1, multiply her by -6, add the result to row 2. Make that a little clearer. What's going on? So that will give me a result where row 1 is unchanged. And row 2 looks like this. Let's divide row 2 by -35. And that will give me a result where row 1 is not changed, but row 2 now has a leading 1. That's a wonderful thing to do. Now let's take a 0x copy of row 2, multiply it by -6, add that to row 1, and that will become the following. But that's the same thing as this. And the creature to the left-hand side of the vertical bar is an identity matrix. So I have exactly what I want. So this is in reduced row echelon form. So the corresponding set of algebraic equations starting from the bottom and going up are that y asterisk is 3/7 and x asterisk is 10/7. So I have my least squares solution. Least squares solution to the problem. It is the vector x asterisk that looks like this. And now I'm in a position to actually physically ask myself, what does this thing mean? So let's go back to a nice simple sketch of the original 3 lines. This is -2. Excuse me. There's a line here that intersects this at the point 1. And there's another line here. So what I have discovered is, while these 3 lines do not intersect each other, so there's no exact solution to the problem, there is a point that's closest to the intersection of these 3 lines. And that roughly is about here. If you just look at that visually, that kind of makes sense. Okay. So it's a good approximation, or it's the best you can do in terms of figuring out the intersection of those 3 lines. It's clearly an approximation. It's not an exact answer. But the method was never intended to give you an exact answer. There is no exact answer. You're getting an approximation. You could compute the error in this problem. I've outlined how to do it previously, and there are examples of how to do this in problem set 13. Excuse me. Okay. So let me conclude today's lecture with the second and final problem. Example 2 of how the least squares solution to a problem is useful. So here, I want to consider 4 data points, well, really 4 points. What makes them data points is a particular application. So everything we're going to do now is independent of an application. So it makes it more powerful. It's general. And I'm going to make my life very simple. I'm going to stick to the plane, R2, and I'm going to pick 4 points, V1, V2, V3, and v sub 4. And let me plot these points. Here's one. Here's another. Here's another. Where this is 1. This is -1. This is 1. And here's point 2. So, first question, can we find a line that passes through all 4 points? And the answer is no. And you clearly can see that. This point, 3 of these points are fine, but this other point is off. So that doesn't mean we just stop and go home. Can we find a line that best fits or approximates our 4 data points? That's a different question. And the answer to that question is yes. And what this involves is simply finding a least squares solution. So let's roll up our sleeves and get started. So the equation of a line is y equals mx plus b. Y is some function of x. And I don't know what m and b are, but I have 4 data points. So for each one of these data points, let's say v sub 1, I know that x is 0 and y is x is -1 and y is 0. So this would satisfy the following equation. V sub 2, I can see that that solves an equation where I know that x is 0 and y is 1. So I would get a second piece of information. V sub 3 satisfies the equation of a line where y is 2 and x is 1. And finally, v sub 4 will satisfy the equation of a line where y is 1 and x is 2. So I have all this information here. What's the information I have? Oh, I have, let's see. I have this piece of information, but I could rewrite this. So let us recast these 4 equations as a matrix equation. Let me write it out differently so you can sort of see where this is headed. Here's one equation. Here's another equation. Here is another equation. And here's my 4th and final equation. So I could write this as a matrix equation. Let me just write it out first and explain what these guys are in a minute. So just recasting data a different way. Here's the matrix A, here's the vector X, constant matrix B. Let's see if these guys are compatible. 4 by 2, 4 rows and 2 columns. A. B has 4 rows and 1 column, and X has 2 rows and 1 column, so they are compatible. So here is a matrix vector equation. Really, it's a hard linear algebra. And I want you to show, using Gauss-Jordan elimination, that this problem has no solution. Now, I really didn't need Gauss-Jordan elimination, right? Because if I looked at the plot that I generated a few minutes ago, clearly this point is the problem. This prevents you from writing a line through all 4 points. But again, you don't just give up and go home. You ask the question, does this problem have a least squares solution? Namely, can you find a vector A asterisk that satisfies that equation or the normal equation? And put the normal equation in a rectangular box to highlight its importance. This is our normal equation. And so we want to solve this for X asterisk. Okay, so I'm going to set this up and I'm going to leave the details for you. To in fact prove. I need A, which I have. I need B, which I have. I need the transpose of A, which I can write down. I'm going to need the matrix product of the transpose of A times A, and that's going to be the following matrix. Again, eagle-eyed members of the audience recognize that this is a symmetric matrix. This is not an accident. And then finally, I'm going to need the transpose of A times B. And that's going to be a matrix that has 4 rows and 4 columns. So what is my normal equation? My normal equation is that the transpose of A times the least square solution equals the transpose of A times the vector B. And take all these results And I can write down a matrix equation where M asterisk and B asterisk are the least square solutions to my problem. They will describe respectively the slope and the y-intercept of the line that best approximates going through those 4 pieces of data. Gauss-Jordan elimination is going to come to our rescue again. We can solve this problem by writing down an augmented matrix. Let's see. Let us take row 1 and divide it by 2. Let us then interchange row 1 and row 2 so that the 1, 1 matrix element of this 2 by 3 matrix is 1. That sets us on the path to reduce row echelon form. Let's take a Xerox copy of row 1, multiply it by -3, and add that to row 2. So as needed, I will get a 0 underneath the leading row of the leading column here, which I need to if I want to put this in reduced row echelon form. Let us divide row 2 by -5. And then let us take a Xerox copy of row 2, multiply it by -2, add that to row 1. And you should be able to show that these are the matrix elements you get. And I now have my augmented matrix in reduced row echelon form. So the corresponding set of algebraic equations is simply going to be, starting from the bottom and working my way up, B asterisk will be 4/5. M asterisk will be 2/5. And we're home. Our least squares solution is that we, excuse me, we now know, I'm sorry, excuse me, we now know how to write down an equation for the line that will best fit those 4 pieces of data. And that's just y equals 2/5 x plus 4/5. So let's go back to the original plot and see if we can graph what's going on. Excuse me. So here's the x-axis, y-axis, here's -1, here's 1, 2. I'm not drawing this to scale. So there's 1 data point there. There's another data point here, and here's a data point. So in fact, there are 4 data points. I'm going to stop for a minute and take note that this point is -2. And the reason why I'm doing that is that if you in fact take this equation for a line and graph it, you will get You won't get that. Sorry, it's a little sloppy. Let's clean it up a bit. So here's -2. So here's one data point there. There's another data point there. Another data point there, and there's a data point there. And so what I was trying to show before is that in fact, you get a line that looks like that. It intersects the y-axis at 4/5. And this line is the best you're going to do in terms of coming up with a linear fit to explain these 4 pieces of data. And it's not bad. There's no exact solution, but that doesn't mean you should stop and quit. There's an approximate solution, and the least squares approximation gives you the least squares solution. There is some error, and you can calculate that in the problem set. I've given you some examples of how to do that. But this is very helpful because you can imagine problems where you have huge amounts of data that are scattered all over the place. And if you look at this data, there's some correlation among these various data points. And there is some line that you could compute, which will best explain this data. Again, this is not drawn to scale. And that line would be from the results of a least squares solution. Okay, so the solution to problem set 13 should be online probably within 5 to 7 days. Again, the purpose of the course is at the end of the day to put copies of all the video clips of the lectures, all the problem sets and problem set solutions online through a YouTube link. That's not been done yet, but that will be done at some point in time in the future. So this is the end of the story. I should point out that if you look at problem set 13, for those of you who are interested in where we go next, I have listed a short bibliography of books and resources on the web that I've consulted in building the lectures and problem sets of this course. As advertised, this was meant to be an introduction to linear algebra using Python. And I would encourage you, if you want to learn more about linear algebra and its applications to machine learning, data science, and quantum computing, those references that I've cited at the end of problem set 13 are a good place to start. In terms of Python, you have now dipped your toes into the lake of Python at a very rudimentary, elementary level, at least regarding applications in linear algebra. There's more to Python than what we've covered. And people sometimes ask me, well, what's a great book for using Python? Well, right now, you have gone through a lot of the elementary ideas of how Python works in terms of its syntax. There are other books out there that are available, and there are a lot of sources online that are available. So it's really your own personal choice where to go from next. And again, I encourage you to reach out to me with my email address if you have further questions on any material we've talked about throughout this course. and I'm available to answer these questions even beyond the summer. So thanks very much for your interest and participation, and please enjoy linear algebra and how to use it using one particularly popular structured programming language, Python, which has an advantage over MATLAB and Mathematica in that it is free. Thanks very much.